We'll begin by exploring what's called the determinant of a matrix, which is a really important value in a lot of applications associated with a particular matrix. Now, something that you need to note about a determinant is that it's a number that is going to be connected to a matrix, but notice that it's only connected to matrices that are n by n matrices. So in other words, we're not going to be able to determine determinants from rectangular matrices where like the number of rows is 7 but the number of columns is a different number, like 4. So we can only have square matrices involved when we're dealing with the determinant. And so the notation that we use for a determinant is a couple of different things. So sometimes if you have a matrix, let's say that's capital A, and you're trying to find the determinant of it, then you would say determinant, DET to abbreviate, of the name of the matrix, and then it'll equal whatever the number is. And then another way that we could specify or use notation for determinant of a matrix is to put bars around the name of the matrix. So it looks like right there that it looks similar to absolute value, right? Because we also use bars for absolute value. But note that it doesn't mean absolute value right there. So we're using the bars to mean something different than absolute value, even though they're using the same symbols there. So this is a couple of common ways that we'll express the determinant of a matrix. So we'll mainly focus in on finding the determinant of a 2 by 2 and 3 by 3 matrix. So to begin with, just how do we find a determinant of a 2 by 2 matrix? So to be able to find the determinant of a 2 by 2 matrix, if the elements that you have are labeled as I have it, then the determinant of that matrix, and I'll put capital A because that's the name of that matrix, will be taking the product of A times D. So what's happening right there is you're actually taking the product of the two numbers that are in that diagonal, and it turns out that we consider that to be the main diagonal of the two diagonals. So this other diagonal right there, that's, I don't know, not the main one, it's the other diagonal, I guess I'll call it. And so you actually do want to multiply the other diagonal numbers together, so B and C are in those positions, and then you subtract. So it's really important that you multiply the two numbers in the main diagonal first, and then subtract from that the product of the two numbers that are in the other diagonal. So whatever number answer you get from that is going to be the determinant of that particular matrix. So some examples to show you how we can come up with the determinant. We'll go to L first. So you would take the product of the main diagonal first. So you would take 2 times 1 first, which is 2. And then you would take 7 times 3, which is 21. And so I always like to do that. I like to write the two numbers, and then I always know I'm going to subtract, and then I put the subtraction symbol there, because it could be easy to like mess up negatives and stuff. So that just kind of helps me personally. So then, yeah, 2 minus 21 is negative 19. So negative 19 is going to be equal to the determinant of matrix L. And then for matrix M, if you take the product of the main diagonal there, that's going to give you 60. And then if you take the product of the other two numbers in the diagonal, 4 times negative 7 is negative 28. And that's where this is really important, because if I write the two numbers separate, and then I always make sure I write the minus sign, then, like, especially in this case, we're going to end up adding, of course, because you're subtracting a negative. So when you do add, you get 88. And so that equals the determinant of M. So notice right there that I kind of used the two different notations. When I did the determinant of L, I wrote DET, and then there I put the bars around M. So either way is totally fine. And then one more example with N. So the product of the main diagonal there is negative 15, and then the product of that diagonal is positive 16, because you're doing negative 8 times negative 2, and then you subtract. So now if you do negative 15 minus 16, you're going to end up with negative 31 is equal to the determinant of N. And then just down here at the bottom are a couple little bit more extensions to determinants. So with the first problem here, it asks us to find y if not absolute values. So the determinant of the matrix A is equal to 17, right? So if you think about how you find a determinant of a matrix, right, you do take the product of the main diagonal. subtract the product of the other two diagonal numbers. So we know actually that the determinant is supposed to be 17, right? So that when you take 15 and then 1 times y is y, and you subtract them, we're supposed to get 17, right? And so then obviously right there you just need to solve the equation. So if you subtract 15 from both sides, then negative y is equal to positive 2, and then you can multiply or divide both sides by negative 1. So it turns out that y should be equal to negative 2 then. So basically just saying that that number right there in the matrix has to be the number negative 2 if the determinant of it is going to come out to be 17, right? And then one more sort of problem involving determinants here. It says, for what values of x does the matrix have a positive determinant? So we can see that x is an unknown value in the second row, second column of that matrix. We want to know what values x could be so that the determinant is just some positive number, right? So if you think about what it means for something to be positive, it means it's not negative, nor is it 0. So it needs to be higher than 0, right? So the determinant of it, of course. So the determinant of this matrix is going to be taking the product of the main diagonal, which would be 6 times x, and then subtracting 3 times 9, which is positive 27, away from that, and that's going to be the determinant, right? So if this is your determinant, and we want it to be positive, then we want the determinant to be basically greater than 0, right? And so then based on that inequality, now we should be able to solve and isolate x. So if we add 27, then 6x is going to be greater than 27. And then we can divide by 6, and that's going to give you 4.5. So that means that x could be any number that's greater than 4.5, not 4.5. It could be 4.5000001, right? But any of those numbers then could be a value that we could put inside of that matrix, and then that matrix would have a corresponding determinant that is going to be positive.